All right. Good morning, good afternoon, depending on where you're connecting from. Welcome to UBC ARC online webinar series. My name is George, and today my colleague Wade and I are going to give a 60 minutes presentation on unlocking the power of databases, the introduction. And our colleague Gabe is going to facilitate questions. And today we're going to highlight the importance of databases in research, as well as their application. And this session is going to serve as a kickoff session because in October, we will be hosting some hands-on database training. And in this training, you will learn how to build a database from scratch, and we will be providing a platform for you to do things like this. And we have a lot to cover today, so it's better to get started. We'd like to acknowledge that University of British Columbia Point Grey campus is located on the traditional, ancestral, and unceded territory of the Musqueam people. University of British Columbia Okanagan campus lies on the unceded territory of the Sioux peoples. Some housekeeping items. You have been muted already when you entered this room. This webinar is being recorded. The recording will be made available on ARC YouTube channel. The slide deck for this session is available in ARC technical user document. Can someone please paste the link in the Q&A? You can ask virtual questions in Zoom Q&A. There is an optional 15 minutes Q&A session after this presentation. Feel free to stay and interact with us. We want your feedback. After leaving this workshop, please take a moment to complete a 3-question feedback survey in a pop-up window. Today, we are going to cover 4 topics. First, we are going to introduce some basics of databases. For example, the definition, the database management system, i.e. DBMS, and different types of commonly used databases. Then we're going to review the importance of databases and why you want to consider databases for your research. We will be giving some examples and show how to utilize database to solve practical research problems. Finally, we will be giving some tips and help you choose the right database for your research. Now I will hand over to you, Wade.
All right, thank you for that introduction, George. As he introduced there, my name is Wade Claver. I've been with the university for, a dozen years now, and before that, I worked for a number of high-tech startups where I did a lot of database in practice. This section here, we're just going to give a brief run over sort of all the terms you'll hear around databases, what they are, what a database management system is, and what are the different types of databases you'll hear about and perhaps encounter and want to bring to bear on your particular research problem. Next slide, please. So I always think it's useful to frame database. We tend to think of them as a very technical construct involving computers and that sort of thing. But I think it's useful to frame them in terms of some real world analog examples, if you will. I've got a couple here. We've got our card catalog from what appears to be a very big library. This is for the older people in the room, what you may have looked up, used to look up a book in a library if you visited as in the pre-computer era. And then on the right there, we have, the good old-fashioned Rolodex. But of course, life is full of these types of examples. We have, recipe boxes, and an encyclopedia can be thought of as a document database. It has an index and a number of different articles indexed therein. So it's essentially a document database. So just to keep that in mind as you're going on, we're not doing anything too actually computer oriented here. It's more we're using computers to take these types of constructs and index them faster and allow them to store greater things. As you can imagine, that card catalog is not exactly a quick process. Next slide, please. So one thing we do need to introduce is the idea of a database management system. And in the computer world, it's really important that we sort of keep these these two concepts separate. Database is really just some construct that stores all of your data in some way that is, findable. Maybe we have some ability to do things like you'll hear the term CRUD, C-R-U-D, which is create, read, update, and delete. These are the things we want to do to databases. So essentially, a database is where all that data lives and is stored and is managed. And then our database management system is the user-facing piece that allows us as users to manipulate those databases and put data in, take data out, query them, create new ones, destroy old ones, these sort of types of things. So when you hear something like SQL Server or MySQL, these are in fact database management systems that allow you to manipulate the underlying databases that they've provided. Next slide, please. So the next few slides, we'll talk about the various types of databases that we tend to see. And sort of one of the major types is a relational database. This has really occupied the database sphere for the last 40 plus years. Most of the databases that were in practice and in use when most of the database research and science was being done and people were pursuing careers as DBAs or database administrators, a big chunk of them were relational databases when people we're talking about databases. If you heard somebody say the word database in 1989, this is probably what they were talking about. And the whole idea is that your data is organized into large tabular structures. These tabular structures have relationships to them. And I have some, sort of an example displayed here on the screen. This is part of what they call an entity relationship diagram. And it basically carves down all those things that we've seen in sort of text-based interfaces on computers, whether it's that card catalog in the first example that's been digitized, or an HR system. We have this idea of records that tend to relate to each other, and they go through a process called normalization, where they try and break out all the different types of data that can be related to a particular thing. In this case, we have an employee ID. We have, who they are. I think they could probably do some more work on this example and maybe break out an address record and these kinds of things, and then relate it back to the employee ID. But what you end up with is a large, rigid structure with very predictable fields and a number of tables that relate to one another in a very predictable way. And because of that, we can do some very well-defined queries on them. And you query on things like a key. So employee ID in this example looks like it's a pretty good candidate for a key to get most of the data out of this database. And then moving on, we have the non-relational counterparts that have come along in more recent years and risen to popularity. So if you'll give me the next slide, please, there, George. You'll hear the term NoSQL. In the prior example, the relational databases, SQL refers to the language that's used to put data in and take data out of those databases. So it's a symbolic query language. We've come up with the term NoSQL, and really when they say NoSQL, what they mean is non-tabular, not non-relational. And non-relational isn't really fair because it is data. There are relationships in the data, but the term NoSQL has sort of become a stand-in for everything that's not one of those large relational databases. So rather than having a table-based query structure, they tend to organize data into constructs that are more befitting the situation at hand. Not everything's an HR database. So in some cases where you're, dealing with web content or social network relationships, these kinds of things, there may be a better choice of representation. So we've decided to organize data in terms of maybe graphs, key value pairs, that kind of thing. And because of that, they can be a little bit more flexible. You'll see the point on here that schema is not necessary. Schema refers to the definition of all those tables and how they relate to each other. And then something like a document database, it's just a document. That's the end of your schema. The document can, in essence, be self-describing. So these can be used for all kinds of different data. A lot of them are driven by the sort of changes to the way we write software and the code revolution. So perhaps maybe we want to represent data in a way that's more available to the programming languages that we're using rather than having to parse text all the time, for example. So next slide, please. The simplest type of these NoSQL databases is just a key value pair. I don't know how to describe it better than that. You have a key and you have a value. These might be called hash tables, for example, in computer science speak. And these are analogous to some of the programming features that you may be familiar with if you've worked in any number of programming languages from PHP to Python. Associative arrays, hash maps, dictionaries, these kinds of things. And in essence, they can be very quick because they don't do much. You have a list of keys. Those keys can be indexed some way programmatically so that you can search them very quickly. So search times in a key value database, if you're looking up a key, can be, generally on the order of the log of the number of entries in the database. There's some parts that don't work so well, though. If you want to search for a recurring value amongst all the keys in the database, it becomes a fairly slow operation because now you just have to query the entire database and look for whatever relationship you're looking for in the values. So not ideal in all circumstances, but in certain situations where all we care about is a record of information associated with a collection of individual keys, these can be very quick. Next slide, please. As I mentioned in the introduction to NoSQL here, document-oriented databases are a very popular choice now. And this is driven in many respects by the modern programming models that we use. In these cases, the database just stores a collection of documents. These documents can be anything. And for those of you who are familiar with something like XML or JSON, these documents tend to be self-describing data, and they have most of their indexing values built into the data themselves so that we can do queries on them. And these can be really important for programming, and they can be an excellent choice. JSON, for example, JSON actually stands for JavaScript object notation. It was originally came about as a way to store the state of a JavaScript object in a human readable form or in a textual form that we could easily store, manipulate, and retrieve. So the way we tend to do programming for the web now is a heavily document-oriented endeavor. So this type of database may be an ideal choice for a scenario like this. Or perhaps what you're storing are actually documents in the way that we think of documents, scientific papers, or I'll go back to my recipe, a recipe index example. These are a good choice because you're not necessarily doing anything special with that data other than retrieving it in whole. In which case, maybe you don't need all of that cumbersome framework of a DBMS wrapped around a traditional relational database for that kind of situation. And I guess a nice bonus here is you don't have that rigid schema requirement. So the documents can vary significantly from document to document. The fact that they're a document is all that's necessary for them to go in here. And I imagine there'll be, thanks, George. I imagine there will be some questions. I do have a section at the end of each section here if you have any burning questions, if you think I missed something here. Now, there's also the concept of GraphDB. Now, graph databases are databases that you use when the really important meat of your database is the relationship between objects. So this takes inspiration from the mathematical notion of a graph, where you have nodes linked by edges or vertices, as the math language may be. I have to admit that I've never actually operated a GraphDB. I was a bit of a database junkie for a while, and I definitely looked into them, but I just haven't had a use for them. And now I see the sort of the driving use case for graph databases is funnily enough, social networks. A network is just a graph. So companies like Facebook will use something like a GraphDB in order to store all the relationships between you and your friends and your likes and dislikes and what you visited, what you've clicked on, in order to build up a graph of potential identifiers and descriptors of you. And the bonus for graph databases is these traversal operations that we use to go through them are very quick. There's been a lot of research into them. So we can quickly query all of the vertices between you and something we're interested in. What should I be advertising you sporting goods equipment or hockey equipment coming up to the hockey season? These types of queries can be represented by traversing all the edges between you and the interest stories that you've clicked on, and because of that, they can come up with a weighting to suggest that, oh, well, maybe he likes hockey. Let's try it. So they're a very interesting concept, but very special purpose, I would say, at the same time. And our next one there, George. Now, time series or real-time databases are a rather interesting case of database. In many respects, they can be almost identical to any of the other databases we've talked about, with the sole difference being that they're optimized for storing and retrieving time-stamped data. And in general, they tend to follow timestamp data that is fairly uniform. So if you can imagine, I have some example timestamp entries down here that is, some kind of sensor telemetry. We don't get a lot of variation in the data. We don't get necessarily a lot of relationships in the data, though we may have, right? We may have a separate table that maintains a sensor ID and its location, or who owns it, or what company it's associated with, that kind of thing. But in general, the actual meat of the database is a constantly changing set of time series data. And the real-time handle or real-time description is actually quite apt. These databases can often be optimized around providing up to the last update accurate information. So in database land, one of the types of queries we may want to do is called an aggregate. Aggregates are where we take a whole bunch of information and boil it down to one number, and one everybody's familiar with is an average. So we want the average of all of our sensor readings, perhaps over a given period of time, say a rolling average, the last 5 minutes. Well, real-time databases, if you think of that in terms of an industrial context, can all of a sudden play a very important role. I want to know what my average temperature in the building is over the last 5 minutes, and I'm querying that constantly and using that to provide feedback to a climate control system of some sort. You obviously need that data to be accurate, and it better be the last 5 minutes, not the last 5 minutes from when you decided to flush stuff to disk last or something like that. So I think this type of database maybe has some very important research applications for people doing a lot of live sensor data and needing that real-time, up-to-the-minute picture of what the environment looks like. Yes, cloud-based databases. So this slide really just exists in recognition of the fact that the cloud is a thing now. People are looking to cloud providers to maybe ease their entry into certain products or allow them to roll out a solution without having to capitalize all the hardware that's necessary to offer it. Perhaps they don't want to tackle things like high availability all by themselves. So the major cloud providers have, recognized that database as an important part of people's IT infrastructure is something that they should be offering. So most of the different types of database offerings I've talked about so far are available in a cloud context. And some of the benefits you can quote are things like, cost savings. If you don't have to buy that server and you don't know if you're going to be using the database long term, don't spend $20,000 on a piece of hardware to spin up your database just to find out that it didn't do everything you wanted to do. Or maybe you want to be able to scale the read workload of that database in real time as your customers come and go throughout the time of day. And cloud offerings often have that type of benefit. And then, of course, they maintain the physical security of the environment as well, which can be, challenging for people, especially in maybe a higher ed environment where a variety of people who may or may not be involved in your project have access to spaces where hardware would live. Important to keep in mind, though, it doesn't do everything for you. Just because it's in the cloud, you still have to manage it. So you still have to take on some of that user role, but maybe you get to forego some of the nuts and bolts system administration costs and duties that you would otherwise have to absorb if it were running on your own equipment. Next slide, please. And finally, I wanted to talk about the idea of a data warehouse. It was a fairly big concept back in the 90s, and I think it remains so today. It's just a lot of the warehousing that people interface with is already done by outfits like Google and that sort of thing. But data warehousing just refers to the idea of aggregating a number of databases into a single database for things like online analytics processing. So in this case here, think about a large multinational corporation where they have regional databases to serve regional clients all over the place. And they may do this for a variety of reasons. Maybe they don't want the regional districts to have a complete picture of overall company activity. maybe they have so much data that it would be prohibitively expensive to have the entirety of their database at every location or in every region, or the management of it would just be too much from a personnel side of things. Or maybe it's just there's no business need to have that other than the analytics, which they could do on slower, more expensive gear because they only need to run those queries monthly. In these cases, the idea of a data warehouse is it's just a central point where everything gets pulled into, and then they can do those large, expensive queries. And by expensive, I mean computationally expensive queries that can take a long time, absorb a lot of computational resources, and result in service impacts to the rest of the organization, as maybe point of sale transactions grind to a halt while this large analytics job is happening. So they came up with a concept of data warehousing, where they kind of put a whole pile of resources in one spot and aggregate those regional databases into one locale. And this really applies to any sort of database that we've talked about, whether it be relational or non-relational. And I think our next slide calls for questions here. So I'll stop there, and I'll just put the proviso out there that this is by no means an exhaustive list, given that we can call anything a database, provided that it's basically a piece of information we care about and we have some way to find it. We can call anything a database. So there are other databases that I didn't cover, but I think this is a really good grand tour of the high level of databases.
Wait, we have a hand raised here. Sean, if I have your name correct, do you want to be unmuted and ask, or you can type? Oh, I think maybe the question has been answered. Okay, I guess it's fine. So yeah, thanks, Wade. Okay, section 2, the importance of databases. The objective is straightforward, the benefits of having a database. This is an example of a research cycle. Normally, you will start this by formulating a research question, and then you will consider what data to collect and how to collect your data. Once your data is collected, you will start data analysis. Finally, you will communicate your findings with your audience and answer the initial question. As you can see, most of this is about data. And often you are not the only data consumer in your organization or in your research group. You are part of it. So the question is, how are you going to maintain data accuracy, consistency, and accessibility? Database as a single source of truth is the answer. Single source of truth is a concept in information management that refers to a single authoritative source of all data. It is a unique and a true reference point that everyone in your organization or research group will rely on. If any changes need to be made, you will do that inside the database. So your database is always up to date. When inserting your data into your database, you will have to follow the predefined rules to ensure your data consistency and accuracy. This way, data confusion. I think many of you may heard this before. You are asked to analyze some data to provide some results, but different people came up with different findings. And why is that? Well, the reason is that you people, based on your analysis on different data sets, and the data sets are different. So if you have a database as a single source of truth, and you can avoid this data confusion. Better security control. First one, granular access control. That means in an organization, different people will have a different access to different types of data sets or different data sets. Some people will have a write access, some people has a read-only power. And a DBA will make this happen. Next one, multi-level encryption. Multi-level encryption means you can apply encryption on multiple levels of your data. And the good thing with that is when one layer of encryption is compromised, it won't be the end of the world. For example, you can apply encryption in the database layer. This way, all your data in the database will be encrypted. And if you apply encryption in the application layer, all the data will be encrypted before being sent out. Backup and recovery. Databases come with built-in backup and recovery features. You can easily make regular backups or recover your data as needed. Databases also come with various types of logs. Transaction logs record all the transactions that happened inside the database. For example, the insertions, deletions, and updates you did. Error logs will record all the error messages and warnings. For example, connectivity warnings and permission errors. Audit logs will audit all the interactions with the database. For example, user logins, logouts, and the queries a user committed. Efficient data housekeeping. For those who are not familiar with CRUD operation, CRUD stands for create, read, update, and delete. That is a standard operation you can use to interact with your data in a database. You can apply CRUD operation on one single record, or you can do that to multiple records at once. Database also support concurrent update. Concurrent update means multiple people can connect to a database and do updates. But you cannot do that to flat file based database, for example, SQLite and Access. The reason of that is when the first person logs into a database, the entire database is locked down. And the second or third person can only view the data in the database, cannot do any changes. I have two examples here to show you how this CRUD operation works. First one is SQL, that's for relational database, and the second one is for non-relational database. They are doing the same thing, but with a different syntax. I'm using this one as an example. The first one, you will insert a new record to this table people, and you are specifying the values for each of the field in this table. And the second one, you will list all the data in this table project with the founder being Vancouver Island Health Authority. The third one is going to update one record in this table people. That record has ID being 209, and you will replace the current email value with this new one. The final one is a simple delete. You will delete one record that has ID being 12 from this table people. And just go through very quickly, you will see the syntax are different for non-SQL because that's just what it is. Databases actually have a dual purpose. They serve as both the data storage system and foundations for applications and analytics and even more. Some people may find databases are no longer useful on their demanding need of their data because the data undergoes complex aggregations and transformations. So they adopt and they build data warehouse on top of databases. Data warehouse is a single large data repository that is specifically used for data analytics. If you have a database, you can do something called in-database analytics. In-database analytics is just a type of analytics and that you can do inside the database without the need of exporting data out to a separate analytics platform that can eliminate data movement and reduce processing time. If you want to visualize your data and monitor how your data goes, and you can build dashboards on top of your databases. And so you can use that to identify trends, patterns, and gain insights of your data to support your decision. If you are AI or machine learning practitioner, you know it is important to have databases to support this type of work. You will start with collecting your data, normalize your data, split your data into a training set and a testing set, and then store your data sets in a database. The training set will be used to train your models, and the testing set will be used to evaluate your models. You can build a wide range of web applications using databases, and the databases will be used to store the data that is used for your application. Also will be used to store the data that is generated by your application. We all know ResearchGate is a web application that allows researchers to share their publications and connect to each other. Galaxy is a bioinformatics, a web application. Bioinformaticians use that because it has a rich collection of tools, and it would allow researchers to analyze bioinformatics data and other biological data. What I have here is a small collection of publications. You are welcome to read them through. And this one is talking about database selection. And this is a relational database used in research, in clinical research. And I also have cloud database, document database, graph database. This one talks about migration of relational database to non-relational. Okay, do we have any questions? Actually, I think I may do this. I will leave this question to the Q&A because we are slightly running over time, if that is okay. Section 3, and some examples. There are 4 scenarios: encryption, granular access control, in-database analytics, and the dashboards. So scenario 1, I've collected some personal information, i.e. names and emails. I want to store the data, and I want to ensure that emails are not visible to unauthorized individuals. Since the data is highly structured, only has names, emails, they are text, so I will go for a relational database, and then I will encrypt the email column in the data. So step 1, I create a relational database which has 3 fields. ID is the identifier, and it has name and email. And then I just need to encrypt this column, this email column. So I generate text hash values for this email column using Blowfish algorithm using this syntax. You don't have to use this algorithm. There are plenty out there. You can pick the one you like, depending on the data type you have. Once that is done, I will update this table and apply this hash value to the email column using this syntax. And finally, I will query this table again. And you can see this email column has been encrypted. And the ID field and the name field are the same. Scenario 2. My research group has multiple teams and projects. What I want is to let different teams have access to specific data sets that only relate to their research. And also different people in a different research group will have a different access or different privileges. So I'm going to use Postgres database with access management, assuming I have 2 teams, team 1, team 2. So I create database users for every single one of them. Same syntax with password. The database is called MyDB. So I gave accessibility of this database to everyone. So to John, Tom, Joe, and Chris. Schema is just like a bucket that is used to store data. I will use schema 1 to store data that is only relevant to team 1 and the schema 2 for team 2. So I give access to schema 1 to John and Tom. And Joe and Chris can only access to the data that is in schema 2. So in other words, John and Tom cannot see the data in schema 2 because they are only given the access to schema 1. Then in team 1, I gave John read and write access to all the database tables in this schema. So this person can read and write, and Tom has a read-only power. Similarly, Joe can read and write, and Chris can only read. So up to here, I've set up the accessibility. Now I can go ahead and create my database and insert my data. Scenario 3. My database is in a relational database. My data is in a relational database. I'd like to perform a quick linear regression for my machine learning project without having to export the data out. I'm going to use the technique called in-database analytics. It's very simple. It's simpler than it sounds. So this is the nitrate table. It has a nitrate concentration. Oxygen concentration is stored in the oxygen table. What I want to do here is to compare this nitrate concentration with oxygen concentration. Here is my syntax. I am only interested in slope, intercept, and R-square value. And within the syntax, you will see this nitrate dot something and oxygen dot something. So this nitrate refers to the table name as this one. Reading is the nitrate concentration. Similarly, oxygen is this oxygen table, and the reading stands for this reading column inside this oxygen table. So test is the name of my schema, and I have both nitrate and oxygen tables in the same schema. And I hit run. This is what I got. And it's pretty weak linear regression, linear relationship here. I also have intercept and R-square. Scenario 4, this is a bit of advanced thing, but I just like to let you guys know the database can make a dashboard happen. So my data is in a remote database. I'd like to have a data dashboard and share that dashboard with my colleagues, but I don't have the budget of using a commercial BI tool, for example, Power BI or Tableau. And I don't have JavaScript skills either. How do I do that? Okay, all you need is a VM, virtual machine, or a shared computer that sits in a corner of your lab or your personal computer, and you have no issues with other people accessing your computer. And then you need some free web development tools. And finally, you need a Python. I provisioned a VM using Alliance resources, previously known as Compute Canada. Then I installed Python. I installed a bunch of web development tools, Apache 2, Flask, WSGI. Apache 2 is web application software. Flask is Apache 2 is web server software. Flask is web application framework. WSGI stands for Web Server Gateway Interface, and that is interface between this web server and web application. Once done, I installed a Python Dash. Dash is a Python library that is built on top of Flask and extends the functionalities of Flask to allow you to make interactive dashboard. Finally, I go ahead and did a simple dash script, and then I tested out locally. And you can see this is the IP, and this is what I get. This dashboard is interactive. And if you hover over one of the dots, it will show you relevant metadata. When I'm happy with the results, I can assign a public IP or a domain name and give that to my colleague. Okay, what I have here is a list of commonly used databases, different types, and also examples of DBMS, database management system. When you go from left to right, the data complexity increases. Some people may think non-relational databases are quite difficult. They are more complex than relational databases, but actually it's not the case. So maybe you have not used that. So as you can see, relational database is here. It can be quite complex, to be honest. But what about performance and scalability? Each database comes with its own pros and cons. And so which one is better or the best really depends on the data and how you're going to use your data. So I think the next section, Wade is going to give you some tips and let you know how to choose your preferred database. And so, yeah, again, I think I will leave the question to the end, unless there's any quick ones.
I've been answering some of the questions live.
Okay, cool, great.
Well, responding. As we'll see in this next session here, there's more to some of the answers. There's a lot of things to consider when choosing the right database, and here we are at choosing the right database. All right. Next slide there, please, George. In this section, we're going to talk about sort of the general considerations that go into picking the database solution for your particular problem. And just to be clear, when we have highly data-driven research, maybe there's more than one database solution to be employed. Rarely, is one tool the end of it. We obviously, in our day-to-day lives, no one would ever think you're going to do absolutely everything with a word processor, because you might need a spreadsheet, that kind of thing. And databases are the same. Often our modern IT environments, when it comes to supporting research and academia, these are pretty multifaceted things. They involve a lot of solutions working in concert to deliver the outcome that we're looking at. So in this section, I'm just going to try and give you some tools to sort of help classify your problem, things to think about, how to think about your data, and maybe most importantly, at least know what questions you have to have asked yourselves and have answered prior to seeking help. Because the number of times I talk to a researcher for the first time and we sit down and I actually don't have anything to give them at the end of it, because all I've given them is a bunch of homework in terms of questions that they need to answer before I can actually help them. Hopefully we can help short circuit that process a little bit in this section. Next slide, please. So one of the things I'm always telling prospective database users to do is, think about your data. When I say think about your data, draw pictures. Oftentimes the data really falls into two categories. One is fairly relational. And again, I've got a couple entity relationship diagrams here, which really, help you think about what your data looks like, how it relates to each other, what kind of data you actually want to capture about a process. And ultimately, this is driven by two things: the source of data coming into your project and, the structure of it, and the type of questions that you want to ask of that data. And, once you've got that figured out, then you can worry about the bigger questions in terms of resources, like how much do you have and how much does it change? Because those are real drivers of the magnitude of the computational solution behind it. But ultimately, the driver of the structure in the question isn't really a resource question. It's, do you have the data model of what you're trying to accomplish fixed in your head? Because you really don't want to start building these things and then realize that you left out some big chunk. If you can satisfy yourself on a whiteboard that you've captured sort of all the questions you want to ask of your data and what kind of relationships there are, and where you might be missing data, where you're going to have a lot of change in your data, these kinds of things, then you're far better positioned to actually choose a solution. Next slide, please. There's other things to think about too that aren't just driven by the data. Maybe you've got a collection of expertise within your lab. I saw some pictures. I saw some questions coming up, people talking about Excel, people talking about they've got Postgres and they're looking at Mongo, these kinds of things. And, that is a real consideration. If you're going to go forward with a data model, there is some expense in terms of learning and time and these kinds of things that need to be put in to be able to install, populate, manage, query, all the general stuff that goes into operating a database in terms of, building that expertise. And if you have a lot of that expertise already in your group, well, then maybe that can be of greater value than some perceived shortcomings of your current solution. That said, we are in a higher ed institution. A lot of the work that we do is done by graduate students, and they have this pesky habit of graduating and getting their degrees and moving on and taking all their knowledge with them out of our labs. So, you got to think about that expertise lives in your lab now. It might not be there forever. The other thing you need to think about is, and I just sorry, I'll go back one step. Business continuity. There's a business term that, maybe isn't that prevalent in academia, but when we think of a lab as a data ingesting and research producing endeavor, this is very much a business, right? And you can just tell, you want to talk about the importance of it? Well, let's talk about your, promotion and tenure processes and what happens if you're not producing that research. The spice must keep flowing. And to that end, that database choice and making sure that you have the expertise and tools to carry it on is very much an important consideration. And the other thing I'd urge you to consider is how supported it is. Numerous occasions I've had somebody come to me very excited about this new database solution that works with this new language and everybody's using it, but they're not. Is there a history behind the database? Is it supported? Can you get commercial support? Is it maintained? How many updates have there been? If it's open source, how many updates have there been to its Git repo lately? Is it an active concern? Or are you going to find yourself in a situation where they've stopped maintaining it, there's a security vulnerability, and now you're kind of left holding the bag because you can't run your database solution anymore in the way that you used to because it's not working, and now you're kind of left in a lurch. So these are all kinds of things that need to be considered in terms of selecting a database management solution. Next slide, please. And there's also the data itself you need to consider. And I mentioned in my first slide, I had those nice entity relationship diagrams there, that kind of thing. Well, maybe your data didn't fit that well into that kind of model. And, I said here, if you drew a picture and there was only 2 tables, well, maybe you don't need a relational database to manage something like that. Or you have one table with all your data and a smattering of other tables. Well, then maybe a relational database is appropriate, but one of the things it holds is keys to another database that's more optimized towards the type of data that's held there. And maybe that one table with all your rows would be a very good key value database. And instead of, storing everything in your relational database, the majority of your data could be in some other thing. And how much of a state of flux your data is in is also a consideration. Maybe a real-time database should be considered, or a document database. So, I realize there's no solutions on this slide into exactly, what you should be choosing, but these are the kinds of considerations that you have to be thinking about with respect to your data when you're making that choice as to what database solution am I choosing for the data at hand. I have a second slide here on choosing a next slide, please. Just to know, we have relational databases, and then we have all of these other databases. So when to maybe consider, when that's not the best choice. Relational databases have a lot of machinery around them. Keeping all of those tables in memory and indexing them and maintaining all the relationships and sequences and query statistics does have a lot of overhead. So at some point, once you hit the billions of rows, you'll note that Google search results are not stored in a relational database. It would just be impossible. They would be using all their horsepower just to maintain indexes and none of it to query data. So there is a trade-off. Databases, I put here hundreds of millions of rows for modern relational database. When I started in the industry, and the Mac Daddy of processors was a Pentium 3, and we could get as much as 2 gigabytes of data into some of our systems. Relational databases at that point, we need 2 million rows and you're starting to get near the end. 10, your database is falling over on simple queries. Now hardware has obviously progressed, so hundreds of millions are fine, but it's not a it's not a limitless game. With our ability to acquire data now, we can easily get hundreds of millions or billions of rows in very short order in these log systems. So in those cases, definitely NoSQL is probably the way you want to go. And of course, now there's many to choose from there, but again, that becomes a very data dependent thing. And our final slide there, George, please. The biggest piece of design advice I can give you is seek advice. Ask somebody. You are not the first person to do what you're doing with a database, or at least at an abstract sense, you're not the first person to do what you're doing with a database. So if you have colleagues in your field, ask them. Ask your IT support unit. And of course, you can ask us. Our contact information is available. Should be on all your communications, arc.support@ubc.ca. And while supporting databases isn't our primary goal, we love to hear about research. We love to hear about how IT solutions can be brought to bear on research. And at the very least, we can probably find someone to help you with your particular issue, even if we can't. And advice is easy. I really don't mind having a conversation with somebody, and I think you'll find most of my colleagues are in a similar boat. So do seek that advice. And I think that brings us to the end of our presentation at this point. Again, I know we probably didn't answer every question you might have, but I think at this point, the floor is open for your questions. And feel free to jump on live and ask them in person if you feel so inclined.
Yeah, thanks, Wade. Thank you, everyone, for attending. And if you have any questions, email us or just stay and to interact with us, or feel free to drop off. And once again, in October, we will be organizing some hands-on training, and you will learn practical skills of how to build a database from scratch. So stay tuned. Thank you. Okay, Q&A. What have we got? Okay, thanks, Ron. And we've got no email.
Yeah, and Ron, I did send you a little nudge in on Teams there. No, I didn't see when you had logged in last, so I didn't pay attention to that. Sandra, I can't speak to UBC in general. I know the Center for Teaching and Learning does a whole variety of instruction stuff. As George mentioned at the outset, in October, they're planning to have a far more in-depth database training thing. The problem with database training is as we just covered, database is a big deal. So when you get training that tends to focus on, here's how you build a database in PostgreSQL, or here's how you use Node.js to represent data in a GraphDB scenario. So it becomes very bespoke very quickly. It's really hard to come up with a training that addresses all the questions somebody might have. What we got here? MongoDB store survey results.
Okay, we still have unanswered questions from Eve. Wade, do you have any thoughts on that? MongoDB.
Yeah, so I guess it depends on the survey tool you're using. I'd say that a lot of surveys, if you're using something like what's the UBC tool? Somebody refresh my memory, please. But I know there's a lot of backend querying tools built into a lot of the survey tools. And yeah, Qualtrics. Thank you, Nick. Qualtrics has a number of analysis tools already built into the survey tool. Mongo, oh yeah, and RedCap. Yeah, RedCap also has a whole pile of tools built in there. And I think you can use a lot of R right in the RedCap framework, that kind of thing. When it comes to exporting the data, when it comes to exporting the data and storing it in a document database, perhaps Mongo could do that. I am not a MongoDB expert. I'll fully disclose that right now. It really depends what the goal is. Open-ended questions and surveys are always a hard one. In general, if it's yes, no kind of stuff, and you have a survey ID and you have a number of respondents and you have a number of questions that they get responses for, these are really good relational kinds of things. Just when you get to the open-ended contents, maybe there's a better solution for those contents in particular. It really depends, again, on what kind of questions you want to ask of the data. If it's going to be some sort of qualitative analysis of those open-ended responses, then yeah, you may well be right. Maybe the whole thing could go to a different type of database, or maybe just those contents. If the Postgres database you're using right now is working for most of it, I don't think there's necessarily a reason to throw that out, and maybe you just want to export that data that you're having that's problematic to a different type of database.
And so just to add on to that, I think you can do a text search in MongoDB and use DB articles, for example, find, and to search the text. And also can do geospatial analytics or analysis in MongoDB. And then MongoDB is also machine learning friendly. Some people do machine learning integration.
And if you're kind of already familiar with Postgres, there's all kinds of contributed packages for more rich full text search for all of those geospatial kinds of add-ons as well. So it really comes down to the learning curve. Do you want to tackle a new database? I'll speak to a question somebody had also about the Excel database. They're using Excel for a large database and then having to do some reports. If you're still here, Jeanette, how big, when you say a huge Excel sheet, how many columns and rows, if you're still here to answer that? Because there is sort of a sweet spot there. Excel is really good, but once you hit 10,000 rows or something, it finds some limitations. And then there's a lot of sort of analysis tools that we use to deal with data of a medium size very well programmatically without going to a database management system. For example, R.
I'm around 8,000 rows and maybe 280 columns.
Oh, that won't be Excel then. It won't be a good candidate.
No, it's really tough in Excel, and I feel like it takes a long time. Half the time it won't open properly, and I need a better way. And then when I create my report, I also have a limit on how many fields I can add in a mail merge file. And so once I hit 231, I think it breaks. And so I have to concatenate my cell so that one cell represents multiple pieces of information, and then I can report on it. But it's not fun for me, and I want to switch it up. And I'm just wondering also for the sessions in October that you're planning, what are you going to create your database from scratch in?
Okay, so we are going to provide a digital infrastructure using UBC Edge Cloud. So we will be onboarding people onto this virtual machine, and then they will have the power to create a database. We're going to start with Postgres. So they're going to learn how to do their schema and how to create database and insert their data. So in other words, they will come to this workshop with their scalar data somewhere. And after leaving this workshop, they will have their data in their database and ready for use.
That sounds super fun. I'm wondering,
we hope so.
I'm wondering, should I wait and take your sessions in October before I switch out of Excel into something else, or should I learn?
We're end of June, and if you don't want to wait, feel free to send us an email, and we will look at your request, and if it's okay, you can share some of your data with us, and we can have some people to take a look at it, and we'll get back to you. If needed, we can organize a consultation with you, if that sounds okay. I know October is a bit long wait.
It's okay. October might fit in my cycle, but all of this is great. So thank you so much for this session and for your willingness to help.
Yeah, I'd be inclined to not wait. Mainly because you may get to October and then find out that a relational database is a horrible choice for the particular data you're dealing with, and now you've waited for you've waited for nothing. So yeah, we can get in touch and can take a look at that data and see perhaps what would be a good direction to go. And the other thing again to be considered is sir, what skill sets are present within your group, and what's going to be achievable, because there's some great database solutions out there for any kind of problem, but perhaps they're not necessarily suited to the skills that exist within a particular lab group, for example. Or they require a large degree of technical know-how in order to run with or make usable. All right. Oh, is MS Access a good alternative? Oh, someone answer that.
Yeah, so I would say yes. But again, it's a flat file database, and if you have multiple users and different people will need to update the records in the database, you will have issue with that. So that's one of the major downsides with MS Access. But it is prettier than Excel based on the design and the user experience. So yeah, and if I do know some organizations or companies use Access as a database to run their applications. But if you don't need multiple people updating that at the same time, you can get away with it. But if you do, I would suggest a non-flat file based database.
The thing I'll say in support of Access is Access is a great way to get your feet wet. if you can use Access in an entirely visual manner, but you can actually do some fairly technical SQL-y database stuff in Access. And if you end up coming up against the limitations of Access, at that point, you've done a lot of the legwork that you need to go to a bigger database anyway. So you've thought about what your database schema looks like. And in fact, Access will allow you to export that database schema as SQL, which then you could import into Microsoft SQL, Postgres, MySQL, those kinds of things. And you'll have you'll be a little bit farther ahead. So while I don't particularly like Access as a robust long-term enterprise grade solution, as a way to get yourself going and figure out what your data model is going to look like and how to query it, it's a fairly low lift way to get involved with the data that doesn't necessarily paint you into a corner you can't get out of. A lot of solutions, you end up with such a large investment in effort and time to get onboarded to it that you really start getting really cozy with the sunken cost fallacy, and now you're stuck using this thing that isn't ideal forever. And I would say in defensive Access, you're not stuck. You can always just export it to something bigger, spend a little bit of time to make it work again, and carry on. So that would be my defensive Access. Don't take that defense as an endorsement, because it is not a robust enterprise grade database, nor is it, ACID compliant. It doesn't guarantee consistency in all cases. So that's important too.
Okay, so Jeanette, I think I will lower your hand. Maybe I forgot to do that because I still see the hand there. Okay. All right. Okay, so we are over time. And once again, thank you very much, everyone, for your attendance and your question. And as UBC ARC, we offer a series of training. So stay tuned again, and please feel free. Well, please help us, with this a survey, and it's very short: 1, 2 multiple choice questions, 1 open-ended question, and thank you. Have a nice day. Bye.
Have a good day, everyone. Oh, you can end.